2, 1. All right, so another little quiz or a mini test here on the introduction of electricity for foundational physics, assuming kind of grade 11-ish, okay, or your first physics course on electricity. So let's see if you can knock out these questions. So as usual, I will post up the link to the PDF file. It's going to be in the description below. So you can download it, try it out, and then come back and see the solutions. So let's dive in, okay? On the questions where I'm going to be doing calculations, I'll try to round to 3 significant figures, okay? Unless it's kind of unnecessary. So let's take a look. So first, a few multiple choice questions. Here's the first one. Which statement best captures electric current? So electric current is basically the flow of charge or of electrons and that you have. So let's take a look here. So A, potential energy, no, the flow of charge. Okay, so there we go. Okay, so that's going to be the electric current right there. It is not C and it is not D. So now question number 2. So the electric power can be captured as well. Power in general is just a transfer of energy, or the amount of work that you do per unit of time. So the best one, so from A, it's not B. Well, C is just a unit. So it is going to be A, just by taking a look at this. It is, so the amount of transferring of energy that you have per unit of time. All right, so that's the best formula that captures this. Number 3, electric charge can be derived from, well, electric charge is a fundamental physical quantity. So it cannot be derived really from anything. Okay, so within here, so it's not going to be mass, distance, and time. So although those are physical fundamental quantities, but they cannot come up with charge. So let's take a look which one is best. It looks like C is going to be best. That is, it cannot be derived. It is a fundamental physical quantity. So it's kind of the fourth one that you dive into. All right, so moving on. So question number 4. So 2 alike charges will always, indeed, they will always repel each other. So that is true. Let's see if there's anything else. No, not attract. Have a charge of 0, so not necessarily. Stabilize each other, not necessarily. None of the above. All right, so A it is. Number 5, the charge on one electron is, well, one electron is very tiny in terms of charge. It's like 1.6 times 10 to the negative 19 or 1.602, depending how many significant figures you want to hold there. So it's going to be none of these. So B, for example, I mean 8.99 times 10 to the 9, that's the constant that you have in Coulomb's law, but it has nothing to do with the charge on an electron. So that's that. And then the 6.67 times 10 to the 11, that's from gravitational potential energy. That's the capital G that you have in that equation. All right, so number 6, Coulomb's law finds the energy present. No. Electric field. No. I mean, we can use Coulomb's law to find the electric field at a point from a static charge, but that's not what Coulomb's law finds. So it looks like it's the force between 2 static charges. That would be the answer there. Number 7, the electric field has units of, all right, so that one's easy. So that's going to be newtons per coulomb. So that's right there. And that completes the entire multiple choice. Here's the first question in terms of calculations, or at least some intuition. So this one kind of brings back the efficiency concept. So efficiency of a nuclear plant has been observed to be 39%. All right, well, first of all, okay, so efficiency is equivalent to the energy, okay, kind of the useful energy. I mean, this depends how you're going to be writing this out. So sometimes energy in or useful energy, I'll write just useful energy. And then the energy total that has been used, or the total energy that has been outputted. So within here, now they're telling us that the efficiency is at 39%. So this is times 100%. Now, of course, if you take 39 and you divide it by 100, you're going to get 0.39. So you're going to get 0.39 That's the efficiency in the equation. And we have, so let's duplicate this just so that we have it in there. So that's what we have. Now, if the power plant produces, so that's quite a bit of power, so 3,500 megawatts of useful power. All right, so useful power, so that means we can obtain the useful energy out of that. So please recall, so if we have power is equal to, now this is on the useful side, so I'll put useful, is 3,500 megawatts, which is just nothing else but megajoules per second. So we can obtain what the energy, the useful energy is out of this. That would have been the power that you use times whatever time that you have. Now, they do tell us what is the total energy needed to keep the power plant functioning for 45 minutes, right? So that 45 minutes, which is right there, so let me just highlight all of these in here. So that's the power, that's the efficiency, and that's for the length of time. So that length of time we need because of the fact that, you know, we can take this and multiply it by delta t. Now, don't forget, it's because power is just equal to the change, right, divided by this. And that was actually, I think, in one of the multiple choice questions as well. So I'm using this and then just rearranging for the amount of energy, and in this case, the useful energy in here. So coming back in here, so let's input all of this in. That's going to be megajoules per second multiplied by, and so that's going to be times the time. So it's 45 minutes. Now, of course, you're going to have to multiply this by 60 divided by 1 minute because of the fact that it's per second, so the seconds have to cancel. And then you are going to obtain what the total amount of the useful energy is. So let's take out the calculator here. So 3,500. I'm going to just, so the mega, all right, so times 10 to the, this is going to be 6. 1, 2, 3, 4, 5, 6. All right, and then multiplied by, so I'm just changing this to joules altogether, 45 times 60. So it's going to be an enormous amount. So 9.45 times 10 to the 12 joules. All right. Now I'm going to keep it in SI units, although they are asking the answer to be in kilojoules. So we'll change that afterwards. So we'll worry about that. All right. So this is the useful amount. So that is this right here. So that means if you want to know what the total amount of energy is, so the total energy, E total, is going to be equal to your useful energy divided by 0.39. All right, so you can now substitute everything back in here. So you can substitute this, which I think we have, yeah, we still have it on our calculator, divided by 0.39. And there's our answer. So it's 2.4, I guess 3 significant figures, times 10 to the 13. But of course, this is joules. So now if you want to change joules to kilojoules, right? So you're going to have to move the decimal over. In this case, it's going to be the scientific notation. So it's still going to be 2.42, but instead of 10 to the 3, it's going to be 10 to the 10 kilojoules, because remember, kilos just times 10 to the 3. So that would have been your answer to this question. So that's the entire thing. So it's a little bit of work, but it forces you back into power and efficiencies as well. So it's a good example. That is it for this one. Here's the next example. So this one is more kind of conceptual than it is in terms of calculation. So it looks like it's electric induction. And let's see what happens here. So for the given figure, explain what will happen if the negative charge on the rod on the right side has its charge fixed. So it's incapable of moving. All right, so what that's saying is that this rod, so these negatives are not going to go anywhere. So if they will not go anywhere, and this is the setup. So what actually will happen is that you're going to have these electrons, because they repel each other, right? They're alike. So this is actually going to get kind of grounded. So these electrons are going to move away into the ground. And this, okay, is going to turn. So this is going to actually turn all into kind of positive charges left over, so that these two kind of can balance each other off, right? So in terms of induction, so that's what will happen for this. And that is it, right? So that's all that's going to happen. So those electrons are going to fly out as far as they can because the other ones are fixed. If they both were not fixed, then what would happen is that, you know, these are also would try to move away, at least until the point that there is some kind of equilibrium in terms of charges as best as it possibly can be, right? So this one would have also been kind of trying to shift away, but because it's fixed, then definitely those electrons on the left are going to get discharged into the ground. Okay, so that is it for this one, but it's a good example. Here's the next example. So what I have done is I've actually kind of brought in our equations in here, okay, back, or at least a equation. So this is Coulomb's law, which we're going to be needing for this example. So you don't have it if you downloaded the PDF. You kind of would have to remember this, okay, or if you're using formula sheets, you would be using that for yourself. So it says, find the electric static force present on charge Q1, assuming that the distance there is equal to 1 centimeter, and the charges, all right, so they give us all of the charges. Okay, so let's first begin. So I'm going to just write down everything in here for myself. Okay, so Q1 is 1.5, so notice it's a positive charge of -6 coulombs. And Q2 is going to be a negative charge. Now, notice Q2 is going to be basically Q1 divided by -2. So if you took that and you solved that equation, this is what you would have gotten. So that's going to be 1.5 times 10 to the -6 coulombs divided by 2. And this whole thing is going to turn negative. All right, so that's what we have there. And then Q3 is a third of Q1. All right, so here, this is going to be Q1 divided by 3 is equal to, so 1.5 times 10 to the -6 divided by 3, and this one is positive. All right, so that's the first thing, just so that we have. I'm going to make this a little bit smaller. And then the other item is that the distance, at least that's what they tell us, is 1 centimeter. So I'm going to keep it in metric standard. So that's what we're going to have there. So those are the distances. So now, how are we going to get, so now we're going to be working on this right here, okay, on this Q1. So really what you have is kind of something, I'm going to move the Q1 out here. Okay, so what you have is this. So if this is Q1, you're going to have a force coming from Q2, and you're going to have a force also coming from Q3, right? Now, we can find what these forces are. Now, we also know, so we're going to do kind of superposition, so we're going to do them one at a time. So that means we'll first assume that Q3 is not there, and then we're going to find out what that force will be from Q2. Now notice Q2 is negative and Q1 is positive, so those two are going to attract each other. So, you know, if you're kind of drawing this out, this is going to get attracted to this, right? So the force is going to be in this direction. Now we're going to come back to those forces in just a moment when we're finding this whole thing out. But first, let's just find the magnitudes. Okay, so that's going to be with respect to Q1. So here, what we have, so on this, we're going to have a force, which is on Q1, and it is with respect to Q2. Plus, you're going to have also a force on Q1 with respect to Q3. Now, with respect to Q3, so in that situation, notice that Q1 and Q3, so in this case, they are both positive, so they're going to repel each other. So that means this force is going to get kind of pushed away. Now we'll see how big these forces are in just a moment, but those will be the forces and the directions that we have. So now let's find out what the actual results are. So for this one, so this one right here, so we'll have, so this is going to be K multiplied by, so notice this is going to be Q1 multiplied by, so indeed it's going to be Q2, and then divided by, so I'm going to substitute that in there. Now I know I need to know the distance in here. Now this distance is formed by, this triangle, okay, that you have. And notice this is D, this is 2D because it's D plus D. And now this right here by Pythagorean theorem is going to be D squared plus 2D, right, squared, and then you're going to take the square root. Now the nice thing is that happens because of the fact that you have the distance right here between the two charges that you have in there is squared. So that's when you square the square root, it's going to get rid of that one. So that means this is going to be just simply D squared plus 2D squared, right? That square root is gone because of the square that we have. Now the other component, so that's going to be this component right here. Maybe let me use a different color. So that's going to be our K, Q1. This is Q3 divided by, and you are now a distance of 2D away. Now in this case, because there's no square root, so we will have our square right there. So now we have to find out what these are. So it's just a matter of substituting all of the results in here, right? So we have Q1, we have Q2, we have Q3, and we have D. So I'm going to substitute all of this, and I'm going to find out what the magnitude is, right? So I want to know what this magnitude will be, and I want to know what this magnitude will be. So I'm going to do those in fast forward fashion, okay? So we'll be right back. All right, so we have the two calculations done, so it's about 20 newtons and about 16 or 17 newtons there. So I kept the decimal places within here, but those are magnitudes. So now what we need to do is we need to take our charge, and we have to know, okay, so 1 with respect to 2. So notice we mentioned that those are going to be attracting each other. So in that particular force, so that 20 point, etc., is going to be right here. And this is going to form, so in order to find out, let's break it down into its x component, and let's break it down into its y component right there. So we're going to have both, so this is going to be f, okay, 1, 2 with respect to the x, and then f, okay, 1, 2 with respect to the y. So we know, okay, so this is that value, okay, right there. And we do know the actual, so notice that's 2D right here. So this, we know those ratios. This is 2D, and this is actually D, okay, right there. So we can figure out what those components are. So we can find out what that angle is, and then we can find out the actual component. So I'll do that in a moment. So that's going to be the first one. And then the second one is going to be a little bit easier because that's entirely the x component right there. So that one, because of the fact that they're both positive, Q1 and Q3, so these are going to be repelling each other, and this one is going to be in this direction, right? So that's going to be the F13, and it's purely in the x component, right? So this one is actually 16.85, etc. All right, so we only need to find out those x and y values of the component, which is Q1 with respect to Q2. All right, so let me just find that angle, and then we're going to find out those components. All right, so now we have the angle, so that's just opposite of our adjacent, so we can use the tan, okay, from trigonometry. So we have 26.565, okay, so approximately. And now we can go ahead and find out our answers. So it's going to be 20.2275 multiplied by, this is going to be cos, so multiplied by cos of the angle, which is 26.565 equals. So that component is 18.092, etc. Okay, so that is in the positive direction, and the other x component is in the negative direction, so that's the 16.85. So we're going to deal with those in just a moment. And now in order to find out, so let me just highlight this within here. So that's going to be that x component. Now if you want to find out what the y component is, well, we'll do the same exact thing in here, except we're going to just multiply it by sine. So that's going to be sine of 26.565 equals, all right? And that is the other component that we have. Let me put it maybe in red so it pops out in here. So this is going to be 9.04, 5. Okay, I'm going to round this because of that. So that's in the up direction right there. So overall, this is what we have. So we have this, okay? So in the x component, we have, there's going to be 18.092 minus the 16.85625, right? So that is going to be in the x component, and in the y component, we have just 9.046. Okay, so this is newtons. Now, if I take out the calculator again, let me just compute this out. So 18.092 minus 16.85625. So this one is very small. That's 1.23575. I'm still kind of keeping it, so I'm not rounding it too much. So now those are your x and y components. So if you want to know what the overall force is, of course, you're going to run into this, where you have a component in the x, so that one is very small, and then you have a big component in the y. All right, so there we have it. So this one is approximately 9046. This one is approximately 1.23575. And your resultant vector is going to be this one, right? So now if you want to find out what that resultant vector is, well, we can find the magnitude. That's just using Pythagorean theorem. So within here, so if we had, let's call this, okay, the y component, this is the x component. So we're going to need to find then the y squared plus x squared, and we're going to need to take the square root, okay, in order to find the magnitude of, I guess, the net. All right, that's going to be the magnitude of that. And then, of course, for the angle, you have opposite over adjacent. So within here, so this is going to be 10 of the opposite. So it's going to be 9.046, okay, or in other words, your y over your x, 1.23575, and that will give us at what angle, okay, this is with respect to the positive axes. All right, so I'll compute this out, and then we'll know what the answer is. And there you have it. All right, so it's quite a bit of work with regards to this, but it's a nice exercise. Once again, because it forces you, to go through Coulomb's law and then know what to do with these particular vectors. All right, so that is it for this example. Here's the last example. This one is actually probably worse than the previous one in terms of keeping things in track. So it's the same setup where you have Q1, Q2, Q3. The values are the same as well. So, we won't have to redo that. But they're asking us for the electric field at the origin. So we want to know what the electric field is, okay, right there. Now, electric field, of course, we're going to have to use superposition. So it's going to be, what's the electric field coming from this one, Okay, so from Q1, we're going to need to find out what the electric field, so I'll call this one 3, from this, and we're going to need to find out what the electric field is from this one. And it's going to be the superposition of those 3 that we will have. Now, the only thing is, because of the fact that you are actually, computing it right here. Now, please remember that it's all, you're assuming that this is a positive test charge when you're trying to find the electric field with respect to one particular point. So that way you'll know which directions it will be. So, from Q1 and Q3, that's going to be easy. They're on the horizontal, so, there's no like trigonometry involved in here. But from Q2, again, there is a problem because you have the fact that you are at an angle. But in this case, it's a little bit easier than the previous one because the angle itself is, because it's D and a D. Okay, so you have, D and distance D and distance D. So the distances are the same. So that's going to be at a 45-degree angle. So that's much easier because we already now know what the angle is, so we don't really need to find it, right? Okay, so, well, let's try it out. So I'm going to steal a little bit from the previous example. So I'm going to take my charges, my distances, so that I have all of these already. Okay, so let's get these ready, and then we'll work with them one at a time. All right, so the first one, so with respect to, the electric field number 1, again, we're just finding the magnitude for the moment with respect to this. Now, Q1 is positive, so we know that, the direction is going to be in this direction, right? So that's going to be the direction of E1. So the electric field with respect to charge Q1. So that is now, so it's K multiplied by the charge, so 1.5 times 10 to the minus 6, and then divided by the distance squared. So in this case, it's going to be just D squared. So there you have it. So that's going to be our first one. So let's compute this. All right, so that's the first one. It's monstrous, as you can see there. So now let's find out the second one. So I'm going to go in. This is going to be 2 right there. So this one again, so it's going to be K. Now it's going to take this. I'm going to just take the magnitude of Q2. So let's duplicate it, put it back in there. And divided by, right, so the distance in between. So now notice that the distance itself, because it's a D and a D right there. So again, just a reminder. So we have a triangle, except this triangle is now it's at 45. So this is 0.01, and so is this, right? So in order to find that, so Pythagorean theorem, so we're going to have 0.01 squared plus 0, so plus 0.01 squared again, taking the square root and squaring it, so that means that will be gone. So this is what our result will be. Now, this, okay, with respect to the electric field right here, is going to be in the direction, so this is going to be in this direction because of the fact, all right, so it's a positive and a negative, so it's going to be right there, right? And where you have, okay, this is, D over D, so this is 45 degrees. Okay, so and we're finding what this value is. So let's substitute it and find out what that will be. All right, so another monstrous one, okay, right here. Now, with this particular one, so I am going to break this down already, so I'm going to take this and just find the X and the Y components. So you're going to have your Y component and then your X component right here, because I already have it, and it's not that difficult to be able to find that out. So let's do that. All right, so there you have it. Because it's at 45, that means both the X and the Y will have the same exact magnitude, right? Because it's cos of 45 and then sine of 45 So that is just 1 over square root of 2. So that's going to be identical. So that leaves us the last one in here. And that last one, so that's going to be E, okay, with respect to Q3. So again, so this is K. Let's shift this out. Okay, I'm going to steal this again. So let's duplicate it. So that's going to be multiplied by that and then divided by right here. And now the distance, so from Q3 is also just D, which is going to be 0.01, right? So that's what we have. And then we have to square it because it's R squared. So let's try to compute this out and then find out what this will give us. So here's the answer, and the other part is that this one is positive, right? So it's going to be pushing it away. So this is in this direction right there. And so that's that. So now we need superposition. So we have to sum up all the X values and then get the Y value. Now the Y value is only one item, and we've already highlighted that out for us. Okay, so that's going to be our Y value right there. But now what's going to happen with the X, we have to kind of be careful, okay, in here. So starting with E1, I'm going to assume that this way is positive. Okay, so I have to substitute all of this in here. So I'm going to take 1, 3, 4, 8, 5, 0, 1, 2, 3. Okay, so that's check mark to this. That's to the right. Now this one right here, so coming from this, is also to the right. So I'm going to take that, so plus, and it's going to be 2, 3, 8, 3, 8, 3, 3, 7.36. Okay, so check. And then the last one is going to be subtracting 44, 950, 0, 0, 0 equals. All right, so I have, so my X value is 113738. I'll just keep it. I know that there's a lot of digits in here. This is, you know, newtons per coulomb right here. Sorry, these are all actually newtons per coulomb there. And then the Y value, so we've already stated, is positive. So that's 238, 387.36, again, Newton coulombs. So it's not terrible, so within here, but we do have, so once again, now in this case it's going to be longer this way and then shorter this way. And we can find what the resultant electric field is. All right, so that's what we would have. And then we can certainly find out what this angle is as well, based on these particular values. So again, this is your Y, this is your X. So now we're going to use Pythagorean theorem in order to find out what the magnitude will be. And we're going to use 10, okay, so opposite over adjacent, to find out what the angle is. Okay, so I'll do that and I'll be right back. All right, so, well, there we have it. I hope that I got the calculations correct. Okay, so here's the magnitude, so it's pretty big. Here's the angle that you have in there, so that you can find out exactly what that would be. So now, as you are kind of moving along, okay, in here, so this gives us the electric field. They do ask us, so within here, what if they put a charge, you know, at that origin? Then what would be the static force experienced by that charge? Now that charge is 3.5 times bigger than this, right? So what we would have to do now is we would have to take our electric field. So remember that the force that would be on the charge would have been the charge itself times the electric field present there. Now we know what the electric field is, so we just have to multiply this. So this is going to be 3.5 times, you know, 1.5 times 10 to the negative 6. That's what you have in there, times whatever the electric field that is present there, right? So that's what we would have overall with respect to this. Okay, so I can, certainly do this multiplication, and then let's see what the magnitude will be. The angle will not change. All right, so it'll be about 610 newtons of force. So it's quite a bit of force there that would be present, but it was quite a big electric field. Now, if you want to round to 3 significant figures, you certainly can. I mean, I didn't do it here, but we certainly could do that and then put things in scientific notation if we wanted to. So for instance, we could have said that this is 1.16 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And that would have been newtons per coulomb. We can also use prefixes if we wanted to. So this right here, rounded would have been 11.8. And then, of course, if you use this, you can certainly put this to 3 sig figs like that. And that would have been your answer to the last one. So a bit of work that you have, but I think it's good experience with regards to vectors and then finding out how to do those calculations. Thanks for watching. See you in a future video. Bye, everybody.